Hello, everyone. So, in this lecture, we'll be looking into kernel memory and space, like how operating system allocates space to each process. And then we'll also see how virtual memory helps in efficient management of uh, of the main memory. Okay. So first, let's look at kernel memory. So when we looked at dynamic relocation or like address translation, we saw what happens when virtual address that belongs to a process gets translated to a physical address. But we didn't look at what happens when the OS is running, right? So usually, like the most common thing or like the simplest thing that old operating systems or earlier operating system used to do is they used to switch off relocation when operating system is running. Basically, there is a bit in the processor which is process status, which is in the process status register. So this bits controls the relocation. So when OS is running, so operating system actually turns off or rather resets the bit, make the bit zero, so that relocation or rather dynamic address translation doesn't occur. Okay, and operating system also needs to make sure that uh, process should not change its own base and bound, right? Like because it needs to ensure that a process cannot interfere with other process. For that, base and bound of a process should not be changed by the process itself. Because if a process can change the base and bound, then it can change the base and bound to any value it wants. That way it can access any memory that it wants. So we should also make sure that process cannot access or rather cannot change its base and bound. And another thing is we don't actually need multiple address spaces for kernel because kernel is always fixed, right? So kernel is always fixed for all the processes. So we don't need, unlike user processes which need different segments, kernel can be in a fixed segment. If, like irrespective of which process is running, kernel can be always in a fixed location. And we should also have a way to switch between user space and kernel space, and it has to be done atomically in the sense like whenever system call happens, we should switch from user mode to kernel mode, right? And we should also have a way to turn relocation off when we are actually switching from user mode to kernel mode. So basically, when we switch from user mode to kernel mode, we should turn the relocation off, and then we should automatically change the address to a fixed address where the OS is located, right? We should do these two things in an atomic way. So to do this, hardware provides certain facilities. Basically, the instruction like int or rather interrupt instruction or syscall instruction, when that instruction is executed, processor actually switches the mode of the processor to kernel mode. So this is in this mode, when the processor is in kernel mode, then it can access all the privilege instructions and it can also access kernel memory. Okay, and kernel, like after it finishes uh, servicing an system call or an interrupt, it can return to user mode by using a special instruction called iret. Okay, so here switching from user mode to kernel mode happens in hardware and it happens atomically, right? Processor actually takes care of switching the address space and also turning off the relocation. Okay, so what are these privilege instructions and what are the regular instructions? So these privilege instructions are the instructions that can change. For instance, changing base and bound is a privilege instruction. Okay, so whenever if user mode or when a process is running, if it tries to change base and bound, then if fault occurs, that means processor actually denies user mode process to change base and bound register. Similarly, processor user mode process cannot change, for instance, TLB entries because these are privileged instructions. So these privileged instructions can be executed only when the processor is in kernel mode. which can only happen either through system calls or through interrupts, right? So this is how uh, operating system ensures that a process or like user mode process cannot change base and bound, or it cannot change page table entries, so on and so forth. So there are various privileged instructions. For instance, the instructions related to system call, memory mapping, device registers, IO operations. There are various set of special instructions in x86, or like also in ARM. So whenever these instructions are disallowed in user mode, okay, that way uh, operating system ensures that a process cannot randomly affect operating system or other processes. And also, so the way processor allows execution of these privileged instructions is by using a bit called mode bit. So this bit in the processor says whether the code that is running on the processor is a kernel mode code or user mode code. Okay. So when the mode bit is 0, that means all the privileged instructions are allowed. The processor is running in kernel mode. It can execute all the privileged instructions. So when that mode bit is 1, then none of the privileged instructions will be allowed. Basically, when you try to execute privileged instructions in user mode, processor, most of the times it silently denies, or few times you can get a fault, or rather fault to the operating system. Operating system can kill the process. However, in reality, what happens is operating system actually gets mapped to every process's virtual address space. Okay, so that means let's look at kernel, for instance, like Linux kernel. So here, uh, consider 32-bit address space. So here, top 1 GB of the virtual address space is always mapped to kernel memory. Okay, that means so user mode process, like the page table entries corresponding to the top 1 GB of memory, always maps to the kernel. So user mode cannot access its top 1 GB of addresses, by the way. So if you try to access, you will get a segmentation fault. So that means uh, like another consequence of this is although the virtual address space is 4 GB, user mode process can only access 3 GB, right? Because the top 1 GB of the virtual address space is actually allocated to kernel. So this why this is the case? I mean, this actually makes it really easy to transfer the control between user mode and kernel mode, right? And also context switch becomes easy. For instance, what happens is, so for every process, the top 1 GB is mapped to kernel. So that way, when the context switch happens, so we just change the page table entries that belong to the bottom 3 GB, and we do not change the page table entries of the top 1 GB, because top 1 GB of every process is mapped to kernel, right? So that way, whenever, for instance, a process makes a system call, we just change the virtual address to the code that belongs to the top 1 GB, and we just change the mode. That's it. And the kernel code starts executing, right? And then this is very efficient because, like, and also switch. This also helps caching. This also helps kernel code to be cached so that execution of system calls become way faster. Okay. So yeah, one thing to remember is in modern operating systems, kernel is always mapped into certain region of virtual address space. Like in case of Linux kernel, in case of Linux, the top 1 GB of virtual address space of every process is mapped to kernel. So user mode, so a process cannot access top 1 GB. No, when it tries to, if you try to access like top 1 GB of your virtual address space, you will get a segmentation fault. Okay. You'll be disallowed because the page table entries are set such that, so when you are in user mode, you cannot access those the top 1 GB of your virtual address space. Okay, so in reality, if you look at the memory map of a process in Linux, it looks as shown on the slide. So here, usually the text segment starts at eight, address 80 804800. That's the typical start address, and then all the text segment, data segment gets loaded, and the heap starts at random offset, and stack also starts at random offset. This is called layout randomization. It's called address space layout randomization. It's also ASLR. Like you don't need to, if you don't understand ASLR, you don't need to worry about that. What you need to understand is this place where the stack grows and the place where the heap grows is randomized for every run of the process. So that means when you run the same program twice, the stack may not grow, or the start of stack could be different in two different executions of the same process. Okay, so that is what the random stack offset is. Okay, and and the top 1 GB of the address space is always mapped to kernel, and user mode, or rather user code, cannot access. That means it cannot read or write to these addresses, and if you try to do it, you'll get a segmentation fault. This is what happens in Linux kernel. So in the next part, we will be looking into how efficiently can operating system manage main memory, like how the virtual addresses are filled up by the operating system for each process.